Hey everyone, it's Bradley Bush again with another algebra video for you. Today we're talking about rational inequalities. Our to-do list, first, what is a rational inequality? We'll discuss that. And then we'll talk about how you solve rational inequalities. And finally, we'll give you a worked example. I'll also put the timestamps in the video description so you can skip ahead if you'd like. What is a rational inequality? Good question. So, a rational function, that's probably a good place to start, is a function, we can call a function f, where you have it's a fraction, and you have a polynomial on the top, we'll call that p1, and you have a polynomial in the bottom of the fraction, we'll call that p2. So p1 divided by p2, both p1 and p2 are polynomials, and you've got a rational function. So if you set that equal to 0 or some constant, you'd have a polynomial equation. But if we introduce inequalities, so less than, greater than or equal to, or less than or equal to, instead of an equal sign, then we have a rational inequality. So if we let our function f be a rational function, then that rational function, less than 0, greater than 0, less than or equal, or greater than or equal, those are all rational inequalities. So it's not as bad as it sounds. How do you solve a rational inequality? Well, if you have already learned how to solve a polynomial inequality, it's actually very similar. There's just one extra step. So the first thing you do is you need to make sure you have it written in the standard form, which is everything on the equation, or everything in the inequality on one side and 0 on the other. So if you have your rational inequality, first of all, you need to make sure that that rational inequality is one single fraction, not multiple fractions added together, say 2 fractions or 3 fractions added together. If that's the case, you've got to get them into one single fraction first, and then get them to one side of the inequality and have 0 on the other. I prefer to take my function to the left and have the 0 on the right, but either way works. So the next thing you do is you set p1 equal to 0, which is the numerator, and then you set p2 equal to 0, which is the denominator, and you solve for x in both of those instances. When you solve for p1, which is the numerator, equal to 0, you find the x-intercepts. When you solve for p2 equal to 0, that finds the vertical asymptotes. And these inequalities, these rational inequalities, they only change sign, meaning the function doesn't ever change from below the x-axis to above the x-axis or vice versa, unless it happens at a x-intercept or an asymptote. Excuse me. So we find out where all of those happen, and then we can find where we have intervals, which is step 3. So you take the x values you found in step 2 from setting p1 equal to 0, p2 equal to 0, and you create intervals along the x-axis. You order them, create intervals, and then you test each of those intervals to see if each of those functions is above the x-axis or below the x-axis. And that's really all you do. Let's start by solving this example. So our function that we have is, our rational function is x plus 1 divided by x plus 3. And the inequality is greater than or equal, and we have 2. So where does x plus 1 divided by x plus 3, where is it greater than or equal to 2? Well, the first step is to write everything on the left and keep 0 on the right. So that's what we're going to do. We will start with subtracting 2 on both sides. That cancels the 2 on the right. And now we have, let's see, I'm going to start writing a little bit smaller here. X plus 1 and x plus 3. And we have minus 2. And then we have greater than equal to to 0. So we need to get a common denominator here. So let's move the greater than or equal to 0 to the right a little bit. And let's multiply top and bottom by x plus 3 to the negative 2. That way we're getting a common denominator. We should multiply the negative 2 through the numerator of the x plus 3 over x plus 3. And that gives us x plus 1 over x plus 3 still. That remained unchanged. But now we have negative 2x minus 6 all over x plus 3. And this is still greater than or equal to 0. So we're getting close now. We have a common denominator. We have x minus or x plus 3 in both of these, and it looks kind of weird without a plus sign in the middle. Let me add that. So now let's combine the numerators. So let's take everything. Let's take the x plus 1 and we'll combine it with the negative 2x minus 6, and that should give us what we want. So we have x plus 1 and negative 2x plus or minus 6. So we have a negative 2x and a positive x. So that just gives us negative x. We have a negative 6 and a positive 1. That gives us negative 5. And this is all over x plus 3. And this is greater than or equal to 0. So now we are in the form we want. We have some function, which is a rational function, and our inequality, and 0 on the right-hand side. So we are done with step 1. Step 2. Step 2 says set the numerator and denominator equal to 0. So our numerator was negative x minus 5. So if we set that equal to 0 and solve, we will get all of our x-intercepts. And our denominator was, let's just write this down before we forget, x plus 3. And we set that equal to 0 and solve, and we'll find the vertical asymptotes there. So let's come back to the numerator, or P1. Maybe I should put P1 here so you remember. P1 of x equals 0, and here's P2 of x equals 0. So if we solve the negative x minus 5 equals 0, if we solve that for x, let's just add x to both sides. And that gives us what we want, because now we have x equals negative 5. That might look a little weird to you. If we put x on the left, it might not look as weird, but the same thing. So x equals negative 5. That's where we have a 0, or an x-intercept. Let's look at P2 equal to 0. If we have x plus 3 equal to 0, we subtract 3 from both sides, and we get x equals negative 3. So here is our vertical asymptote, and at x equals 3 and x equals negative 5, we have a root, or an x-intercept. Done. We're done with step 2. We've found the 2 points on the x-axis where we can have a potential change in either above or below the x-axis. So in our function, in the graph of our function. So let's draw those. If I just kind of drew, let's bring out my ruler. X equals negative 5 is right here. If I draw a dashed line, there's a 0 there, and the other one was x equals negative 3. So if this is negative 5, this is negative 4, negative 3 is right there. Here's negative 2, negative 1, and 0. So negative 3 is right here. Let's do another green dashed line at x equals -3. So now we have 3 sections. We can clearly see 3 sections. We have to the left of -3, so that would be -infinity to -3, and we have in between -3 and -5. Whoops, I totally wrote that wrong. We have to the left of -5, and then we have between -5 and -3. So let's write that. And then we have to the right of -3. So -3 to infinity. So we have 3 intervals here. And our intervals, inside of our intervals, the function is either all above the x-axis or all below the x-axis. So let's go find out. Let's do this. We'll test. We can actually visually see that this is the case. And so we could just literally answer the question here. But let's do the algebra and come up with the answers. And we'll come back to this graph and verify that our algebra was correct. So, because sometimes you don't have a graphing utility like a calculator with you, need to do this by hand. So, our test regions, -infinity to -5. So, let's test -6. Let's choose -6 because that's inside this region, right? So the function, I wrote the function over here to help us, -x minus 5 over x plus 3. Let's see. So what is f of -6? That gives us -6, -5 over x, which is -6, plus 3. Negative and a negative in the numerator give us a positive, so positive 6 plus 5 gives us 1, positive, and then -3. So this is -1/3. So this is a negative region, right? That's less than 0. So this is a negative region. Good to know. Let's test the next region. The next region does not have 0. Let's do -4. I always like to use 0 whenever I can because it's just nice. But we'll do that for the last region. So -4. That gives us a -4 minus 5 all over -4 plus 3. Here we have a -1 over -1, which gives us a +1, which is positive. So we're in a positive region. -5 to -3, it's a positive region. And finally, we get to pick 0, because 0 is in the region from -3 to infinity. So f of 0 gives us -0 minus 5 over 0 plus 3, which is -5 over 3, which is negative. Negative region. So where is our function greater than or equal to 0? Well, it is where it's positive. It's only one place, -5 to -3. So you might be wondering, why do I have these brackets here and here in the bottom? Well, the function is positive or is greater than 0 from -5 to -3. It equals 0 at x equals 5. So I have to include -5 in my answer here. If I used a parenthesis, if I had a parenthesis here, that would be from -5 to -3, but it would not include -5 or -3. So I include it with a bracket. I'm not including -3 because there's -3 isn't in the domain of the function. Because you notice if you put -3 into the denominator, then you would get 0. So let's go back up and look. Looks like we go from negative, positive, negative. Let's go back up and look at our graph. So blue is below. So we go below from -infinity to -5, and I've highlighted yellow with x equals -5 because it's 0 right there. And then pink or red between -5 and -3, which is the region we wanted, right? And then blue again below from -3 to positive infinity. So the only region that was pink or above the x-axis or equal to the x-axis is from -5 to -3, and we include -5. So technically speaking, I think I would probably, if I'm just testing a region, I would probably just want to go, I would want to not include the -5, because if I chose -5, it would give me 0. And that doesn't help me to know if it's above or below. But down here with my answer, -5 to -3, I would definitely use the bracket on the left and a parenthesis on the right, because we include -5, but we don't include -3. Hopefully this was helpful. If it was, give me a like, subscribe to the channel, and thank you for watching.